All right, we're going to do 7.2 sample proportion. Before we do that, we'll look at our warm-ups here. What is a parameter? A number that describes the population. It is mu, it is p, it is sigma. What is a statistic? Number that describes a sample. Your s, your x bar, and your p hat. What is a sampling distribution? It's a distribution of values taken by the statistic in all possible samples of the same size from the same population. So we took a bunch of samples of a bunch of samples. What is bias? Bias is when a sample consistently under or overestimates the value we want. It's biased if it's not close to what we want. Statistical inference is using a sample to make a conclusion about a population. And variability when the value of a statistic varies in repeated random sampling. So it kind of talks about these four dartboards here. So segue into that. If we look at this first one, we have very concentrated group, so it's low variability, didn't vary much, but it's high bias because it's still that far away from the center. Letter B, it's got low bias because it's all over the place. They're low bias because they're not that close to the bullseye. High variability because it's spread out quite a bit. Letter C is high bias, so we're far away from the mean. High variability, and we're not even close to each other. It means our data is not close to what it should be, and it's not even all the same. And of course, the ideal is this last one where there's no bias. So everything is, or the target was hit. Low variability, a whole bunch of them hit. That's what we're looking at here. Why do we use samples to make inference about the population data instead of just getting the population data? Well, sometimes it's impossible. You can't get the exact data. Numbers are changing, it costs a lot, people lied, whatever. A lot of different things is why we don't do that. So we're going to go to this website, rossmanchance.com/applets. I have too many S's in there, so when you actually do it, do not type in that. We're going to set the probability to orange of 0.45. Number of candies is 25. Set number of samples 1. Unclick the end. So it should look like this, besides the fact I forgot to change the probability here. So, not that. And my pen is going to work. It's supposed to be a 0.45, but I don't think it looks like that, so I'm just going to erase. So let's leave it like that for now. So, where there. So again, what we should do, probability of orange, 0.45, number of candies, 25, in a sample, one sample. We don't want to animate because it takes forever if it does that. We want proportion of orange, not the number of orange. And they're going to graph it all right here. Make sure you click summary stats. Nothing there's yet. We're not doing sliders or run. Huh. Now we got to all change this. Portion of orange. Yeah, I don't want to do that. So, first of all, click the sample many times. All right. We have a mean here of 0.417, standard deviation of 0.093. So 0.093 is not very far apart. The data is pretty close to each other. And the mean is 0.417. We're talking about the orange ones, and it should be 0.45, so that's not bad either. As we take more and more samples, our mean gets closer and closer. Take a while, but it could get to 0.45. Not quite there yet. And then This is kind of looking normal now. If we did the normal over top of it, it fits somewhat well. It's a little less, or a little less spread out than normal approximation. But we have mean of 0.436, standard deviation of 0.095. The question asked, what is p hat if you have it, or what is the p hat you have displayed? Is it the same as your neighbor? Probably not. Depending on how many times you did it, you're not going to have the same mean, you're not going to have the same standard deviation, not the same p hat. Just because it's there's variability when you sample. All right, we're going to work with this site a little bit more. So we change the number of samples to 1,000. If we can do 1,000, 1,000 means lots. We're going to see how we can describe your set using socks. So let's reset this. We're going to go 0.45, and we're going to increase the sample size slowly. And we want 1,000 samples. So 0.448 and 0.217. And it's somewhat normal. Reset it and change it to 10. And draw some samples. P hat is 0.3, not very good, not close to what we're looking at, but the mean is getting there. Change the number of candies to 25. Oops. Reset it. That's pretty normal looking. That fits very well. The mean is almost exactly what we want it to be. If we hit another one, even closer, you can see shifted a little bit, but it's becoming normal as we get more and more candies. Just jump all the way to the end here. And so you took 200 Reese's 1,000 times each. The mean is 0.452, which is only 2/1000ths away from our mean. Standard deviation is getting much, much smaller just by changing our sample size. So we're talking about that. After we did samples of 100 or 1,000, approximately normal, we saw that graph fit pretty well. Mean of 0.45, close to, and standard deviation is 1.1, or I guess we did more than that, and that's why we got a closer one, or a smaller one, I should say. Again, we did this. The shape was normal pretty much the whole time. The mean was pretty close to the real mean, and standard deviation was pretty small as well. Now, if we change the proportion that we want, let's see what happens. So reset. Now we want to keep it 25 candies, but our proportion is going to change. So this is pretty extreme, 0.05. And wow, this is very skewed right. Should be very obvious. You do, it's staying with that because the mean is lower, so it's going to be skewed right. If we change this to 0.25, it's a lot better. That's, well, a lot bigger. If we were to do that for all the way up to 0.95, it's skewed right. We have a lot of high values. Do it again, and it's getting more and more And it's centered around where the mean is. The mean is not in the middle. We have 0 to 1, mean's not here. So all the way shifted up to 0.96. So, what was the point? The point was, or is, if I can move this page, that'd be great. It's skewed right if we have small proportions, and it'll skew left as we get even more strong proportions. We can see how the p-hat was basically what it's supposed to be. Our standard deviation got smaller when we were normal, actually not normal. Let's go here. According to the data in the first table, what values of n will the sampling distribution of p-hat be closest to normal? We want 25 or highest at least. So 30 is usually our magic number. That's what we use when we do these problems. According to the data in the second table, what values of p will the sampling distribution of p-hat be closest to normal? Well, that means our p has to be in the middle. So our p-hat has to be 0.5, or p has to be 0.5. Since the shape of the sampling distribution of p-hat is based on both sample size and the probability, we developed a rule to determine when p-hat will an approximate normal distribution. All right. If n times p, where n is the sample size and p is probability, we can use these formulas. These first two, and this, we need to really understand this. If the first two things are true, both of them, then our data is approximately normal distributed. And what those two rules kind of do is make sure that our p is big enough, but not too big. And we are back. So this is correct. Data has to be normally distributed, so these two have to be true. And if it's the 10% rule, then we can find the mean and standard deviation. The mean will be mu of p-hat, which is going to be p. So we're estimating what actually the p is. It'll be approximately normal. Standard deviation and sampling distribution is kind of like what we did for binomials, but a little different. Sigma of p-hat is square root of p times 1 minus p over n. That would be our standard deviation. And then we can do problems based off of that. So if this will move. According to a poll, 22% of high school students in the UK say that Dobby is their favorite character in the Harry Potter books. Let's assume this is a parameter value for the entire population of the school. Obviously, we wouldn't really have the whole data for the school, but that's what we're claiming to have. You take a sample of 150 high school students and record the proportion, p-hat. All right, let's continue this problem. First, we need to know that the 10% rule holds. The 10% is, or that our sample is less than 10% of all high school students. I think it's pretty safe to say clearly, don't say obviously or surely, or just clearly, 150 high school students is less than 10% of all high school students in the UK. We can assume that, that's big enough. That means we can find our mean and our standard deviation. So our mean is mu of p-hat, which is p, which is 0.22, 20% that we have, kind of our parameter. Our standard deviation would be the square root of p times 1 minus p over n. Not sure why I don't have it written there. Let me write that up for you. And I drew an awful signal. So it was RP. 1 minus RP over sample size, which is 150. That's how we got that. And again, we could find these two things because the 10% rule holds. What is the approximate shape of the sampling distribution? Justify your answer. is when we break out the tens. We want to make sure that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. So our n is 150. That's our sample. The p is 0.22, and we just plug them in. So again, I want us to keep going until you really see that 33 is greater than 10. Check it off. 117 bigger than 1 or bigger than 10. Check it off. So it is normal because those work out. And we're back again. So we move to the next page of our notes. So suppose we have a sample of 36 instead of 150. Compare the shape, center, spread of the sample distribution to one in parts A and B. First of all, clearly 36 is still less than 10% of all UK high school students. So we can find the mean and the standard deviation. So the standard deviation was 0.034. All right, that's what we got here. But we'll get to that in a second. Now we want to see if it's normal, if we can do anything with it anyways. So n times p is greater than 10, n times 1 minus p. So it's 36 times 0.22 and 36 times 1 minus 22. Neither one of those, while this one especially is not greater than 10. It doesn't work. So this isn't normal. With the sample 36, we just don't have a normal approximation, so we don't really know. If we were to do the new standard deviation, I should do that. So the difference here is it's 36 in the denominator. Yeah, 0.22, 0.78. And when we put that in our calculator and get our standard deviation, and it's double what it was with the 150. So we made it a lot more spread out. So a small town in the UK has only 600 high school students. What is the largest possible sample you can take from this town and still be able to calculate standard deviation of the sampling distribution of p-hat using the method presented in the book? It's just talking about the 10% rule. It's saying that we have to have n greater than or equal to 1/10 or 10% of 600. And we can do that. We know the sample size. So n has to be greater or equal to 60. So then we could find the standard deviation and the mean because we have the 10% rule, even though this isn't normal. Suppose you take a sample of 50 students from that high school mentioned in letter D and find that 16 students say Dobby is their favorite character. The probability of 16 or more students at the sample is lower than 5%. This means more students like Dobby than the national average. The school will change their mascot name to the Fighting Dobbies. Is the school going to change their name? First, 10% rule. We know from this school earlier it was 600, and so is n our sample size less than or equal to 60? Yeah, 16. So we're okay there. We do our tens. So our n times our p, and our n times 1 minus p, and they're both greater than or equal to 10. So it is normal. Our new standard deviation with a sample of 50 is 0.059. Still not as good as the 150, but not too bad. And 0.22 was the mean. Now, when we're trying to find p hat, well, p hat is from the sample. It is 16 over 50. 16 students say they like out of the 50. So our new probability, or what we're trying to find, is 0.32. What is the probability that p hat is greater than 0.32? That's about 0.045%, which is less than 5%. So it would be rare to get that many people. So they're going to change their name to the Fighting Dobbies. And all we did was normal CDF stuff over here with this data. 32 being low, infinity being high, standard deviation, mean. So we have the fighting Dobbies.